Welcome to Foundry by Forge College. Coming off our previous explainer on the foundations of network efficiency and Gulfstream, today we're tackling a universal developer nightmare. We're going to identify exactly what is secretly slowing down your smart contracts and draining your gas.
Okay, so let's just dive right into this. You've been super diligent, right? Your code is written, you've got perfect test coverage, but why does staring at your CI pipeline feel exactly like waiting for paint to dry? You hit enter, go make a coffee, contemplate your life choices, come back, and it's still just churning. Or even worse, why is your contract suddenly costing an absolute fortune in gas fees just to run a basic transaction? Well, today, we're going to fix that.
Here's our blueprint for this explainer. We're covering the bottleneck problem, hot versus cold paths, spotting the usual suspects, the 3 core lenses, and finally building some diagnostic snippets.
So, kicking things off with Section 1, the bottleneck problem, and dealing with mechanical friction.
We really need to start by understanding the core flaw in our engine here, which is the bottleneck. Now, the crucial point is that bottlenecks fall into 2 overlapping categories. First, you've got EVM cost bottlenecks that inflate your actual on-chain gas fees. And second, you've got test run bottlenecks that absolutely bog down your local computer environments. Sometimes they're exactly the same thing, like a heavy function just takes longer, but sometimes it's honestly just bad test design. Like if you're redeploying massive contracts before every single tiny test, that's going to kill your runtime, even if the transaction itself is cheap. Moving right along to Section 2, hot versus cold paths. Let's talk about targeting that friction.
To fix this machine, we really have to distinguish the parts that are constantly spinning from the emergency brakes that rarely ever engage. Hot paths are frequent, they're highly exercised, and they are absolutely your primary optimization targets. Cold paths? Well, those are your rarely executed edge cases. Honestly, spending days optimizing a cold path is totally a waste of engineering time. It's literally like meticulously polishing a spare tire that you almost never use. Keep in mind, coverage tools will tell you a line of code ran, but they don't tell you how expensive it was. Hot paths are where you actually win back your gas in runtime.
All right, Section 3, spotting the usual suspects. Time to find the culprits.
Now that we know where to look, let's identify the usual culprits causing our system to overheat. If your tests are timing out, you're likely looking at one of these 3 mechanical failures. First up is the hot loop SSTORE. This is basically constantly writing data to the blockchain inside a repeating loop, which causes massive runtimes and huge writes per call. Second, we have heavy event emissions. A lot of devs don't realize this, but spitting out a ton of log data is a really heavy lift for test environments. And third, external call churn. Bouncing back and forth between different contracts causes highly unstable timings. Let's be real for a second. Putting a heavy storage operation, like an STSOA, inside an array processing loop is just a brutally expensive mistake. Imagine paying $10 for a tiny bottle of airport water every single time you take a step down the terminal. That is exactly what your contract is doing to your users' wallets. It's crazy. You've got to batch those state updates or use mappings that minimize writes for unchanged values. Which brings us to Section 4, the 3 core lenses. This is our analytical framework. To properly measure these suspects, without getting completely overwhelmed, we inspect our code through 3 specific lenses. Lens 1, frequency. Simply, how often does this actually run? Lens 2, cost per op. Are we using cheap read operations like an SLOAD, or are we using wildly expensive write operations like an SSTORE? And finally, Lens 3, dependency scope. Is this thing touching external systems that introduced a bunch of lag? Now, what's really interesting about this visualization is how a moderately expensive opcode running in a frequent loop completely eclipses a massive but rare calculation. As you can see, an operation that is only moderately expensive but repeated 100 times is vastly worse than a highly expensive operation that maybe runs once a year. It's basically death by 1,000 cuts. Moving on to Section 5, building diagnostic snippets. Let's actually measure this load.
Theory's great and all, but let's step into the workshop. Instead of reaching for super heavy profiling tools right out of the gate, we use this simple 4-step test harness pattern. First, deploy your target contract. Second, deploy a tiny diagnostics helper. Third, invoke a measure call function. And fourth, capture the gas delta. You're basically checking the fuel gauge with gas left before and after the operation. You want to establish this baseline before you change a single line of logic.
By feeding varying inputs into our snippet, we can immediately spot linear growth in gas and storage writes. This proves exactly where our hot path is leaking efficiency. Look at this example for a distribute rewards function. We test it with 10 recipients and then we test it with 100. The gas leaps from 2.5 million all the way to 18 million, and our storage rights scale perfectly linearly from 10 to 100. This near-linear explosion proves the per-recipient loop is our primary bottleneck. So, this brings us to the golden rule of smart contract optimization. Prioritize your optimizations by frequency multiplied by cost per op. You really need to memorize this equation. It prevents you from chasing ghosts, it stops you from wasting time on cold paths, and it keeps you hyper-focused on the metrics that actually matter for your application's survival. Make sure to save your diagnostic outputs, because in the next module of the Advanced Testing with Foundry course, which is Profiling Test Execution and Gas Metrics, we're going to convert these candidate bottlenecks into detailed quantitative profiles. We'll collect per-op metrics and learn exactly how to attribute these gas costs to specific solidity constructs.
So I want to leave you with this thought. Which cold path in your own codebase have you secretly wasted hours trying to optimize? Look, we've all done it, but now you actually have the tools to avoid it. Think about that as you head over to forge.college to explore more Web3 learning programs. Thanks for tuning into this explainer, and I'll catch you in the next one.